we might as well go ahead and get started. It's about 6 p.m. anyway. For any of those who remember our last episode, we left starting to throw in and define our inputs, some of our pin assignments on the ESP32. Now, I'm hoping that our ambitions as far as the block diagram we threw together aren't too great to where we don't have enough GPIO pins for everything, because the fan with the TAC and the PWM input's going to take up two. The RS-45 communication will run in half duplex. It's going to take up a minimum of two. The stepper driver, that one's going to consume multiple pins, depending on how we want to wire it up, because there are so many things we can control on it. You have an enable pin, a direction pin. You have three micro-stepping pins. We can either choose to control them via the ESP32 or with jumpers. If we control them with ESP32, that would give us more flexibility in our programming, as we can have it switch on demand. There's also a reset pin, an enable pin. So the stepper driver has multiple inputs. So we need to really consider what we want to control. Worst case scenario, absolute worst case scenario, if we absolutely want all these additional features, all the limit switches, control inputs, all the controls for the stepper motor, we could look at like an I2C port expander and just put all your general GPIOs on that port expander and just have a task that scans for that, scans those GPIOs for inputs while maintaining any output that we set. But we'll see. We still have quite a few free here. But that will dwindle quick. So one of the things I want to do is kind of plumb up what I would consider some of the important things before determining, if we want to maybe drop down to just two limit switches. And if we really want the GPIO expander. So let's go ahead and go back to our guy here. Let's copy this guy. Let's go here to Malza. I've selected a couple of tabs up here with other parts that I've been looking at to add, just to make it a little quicker, because I know not everybody wants to really sit here and watch all this stuff, and I get it. So let's get that data sheet opened up. Hey, where'd you open the data sheet? Okay. You can see it here. Little booger. Okay. So let's see here. Stub. Typical application circuit. Let's kind of look. I think we're going to need at least three. But we will have to double check. I may have to dig up another schematic for these chips just to see how we've done it in the past more efficiently. If I'm not mistaken, the ESP32 has a drop-in for our RS-45. They handle the flow control, and I think we're going to need at least 3 pins to manage that, because the drive enable and the read enable pins, they can get tied together. and controlled at the same time, because one direction is active high, the other direction is active low. So it was really convenient. Drive in is basically TX, readout is RX. And this will be on the side of the microcontroller. Obviously, VCC and ground, and then your AB inputs, your differential inputs. So, with that in mind, let's go ahead and just start snagging some GPIO pins. Alright, so we're going to 485 RX. It's going to be an input. .485 TX. It's going to be an output. And come on. And a 485 DIR direction. Get that circled around properly. There we go. You know. All right. So that's our direction. So that'll handle our RS-45. Now let's go over here and kind of determine how we want to use this guy. I'll worry about grabbing that guy later. I'm just trying to do a few things. Alright, let's see here. Pin configurations. So, some of these will go to capacitors, resistors, etc. They don't even go to the microcontroller. Some are no connect, some of them are current detection. So let's see here. Power supply, AREF, BREF, decay mode. That's a control that we can use if we really want. Direction is definitely one that we want. So let's see here. So we definitely want direction. Let's throw this guy in here. Let's see here. What do we want to call this? We can call it stepper. STP DIR. It's going to be an output because we're going to go to. All right, we're going to STP step. Another output. All right. Now, let's see here. We can have it set so we can enable it, reset it, sleep. So the step basically is every pulse it gets, it causes the unit to walk through its internal indexer, which then tells it which motor output to activate at that given step based on the indexer. Reset basically resets the indexer logic and basically sets it back to like index 0 to basically restart the steps. So we can have that enable, which would basically shut down the stepper. Sleep. Not really caring too much about sleep mode to save power, because this is going to be permanently powered. This isn't like going to be something that is typically going to be battery operated. So let's do reset and enable. Let's go and throw those two guys on there. STP reset, which is going to be another output. I'll have to fix that wording. I don't want to. If I leave it go too long. STP enable. All right. We'll assign those pins. Those are outputs. All right. So we have our 485. We have our stepper. And maybe if we're lucky, if we have 2 pins free, we'll throw in basically a generic UART for like a serial console that we can connect to something like an FTDI cable for maybe debugging. If somebody, if you want to throw a debug console on here. So the RS-485 interface would be mainly for communicating to other subsystems, like depending on how you want to program it. Because of the differential nature, you can have multiple devices connected to the same network and have them addressed internally based on their firmware. And that way you can control multiple stepper motors from one central processor, one central system using RS-485 over longer distances than you can get with RS-232. And it'll handle noise better. So that's why I'm throwing 485 on here. We could also throw CAN on instead and use the CAN protocols, but it's a little excessive for what we're looking for. With something like this, RS-485 would be perfect, because then you could control it through PC with a USB to RS-485 converter, and do things like that. So no big deal. So we have. Do we want to allocate 3 pins for the you know what, let's do step microstep. We're going to call it microstep 0. That's going to be another output. STP MS1. There's only 3. STP MS2. Okay. Slap these guys together. Bam. All right. Slap those guys together. All right. That'll also give us, let's see here. So that's our stepper driver. That's step direction, step, reset, enable, microstep 0, 1, and 2. They call it mode, but microstep, it just makes more sense to call it that for me. That way we know what we're setting up, what we're programming. Let's go back. Is there anything else? Decay. Low. That's something we can set with a jumper if we really want it. Like I said, sleep doesn't really matter. Now, fault. So we can have the microcontroller observe the device for a fault if we really wanted to. It doesn't tell you what fault it has. It'll just tell you it's got a fault condition. Let's see here. Let's see. So if we do UART with these guys, like 3 or even 4 control inputs. Yeah, let's go and add that. go FLT. And that's going to be an input. Oop, connect to that pin, boy. There we go. There we go. Okay. So that way we can use the microcontroller to kind of observe for a fault. Like I said, it won't tell you exactly what the fault is, but it'll tell you if the stepper driver is saying, hey, there's a fault condition, if you want to monitor for that kind of thing. I'm sure if we really wanted to, we can look at the current sensing. I think it's got, yeah, it's internal current sensing. We could always throw in current sensing if we really wanted to, but we're not going to go that far. All my testing with this has shown it's really not super important. It's not super important to me, and that would complicate the design. Using a couple ADC inputs, we could technically monitor the current between the motor windings to maybe catch for an overcurrent condition to see how it's drawing, using something like a current sensing resistor set up on it. I'm not really pushing for that with this design because, again, this is just basic prototyping, experimenting. I don't want to make anything too overly complex. The good thing is this chip will shut itself down if it detects a problem like overheating, overcurrent. So it will shut itself down and go into protection mode, and I think that would kick on a fault signal. So we have that fault. So that's our stepper motor. There's a lot of inputs and outputs, a lot of controls on that. That's why we're pin heavy. So let's go ahead. Your RX. This will be like for a standard serial port. TX output. All right. Okay. We're also going to need fan tac. It's going to be an input. Fan PWM, which is going to be an output. Because why not? Let's see. So we have let's see, 1, 2, 3, 4, 5 more GPIO pins. More than I was expecting to have. So let's see here. How many control inputs do we want? Let's say maybe 3 control inputs that we could, use if we really wanted to. Input 1. Input 3. So we have 3 limit switches, 3 inputs, and 2 GPIOs free that we can assign to other things. So we have our serial console UART pins that'll just hook to a standard that you could hook to a standard FTDI cable to. Adapter like USB to FTDI adapter cable. We have our RS-45, our stepper controls, our fan tach and PWM. Now, if you really want to get crazy, we can throw ADCs on, use those two as like ADCs. Maybe double check the data sheet. Might have to move some pins around to see what pins we could use for ADCs. But I don't think that'll be extremely necessary for what we're trying to do. Since it's for development and learning, quick prototyping, I'm not too terribly worried about watching current consumption on the motors. Although it might be fun and entertaining. But it only have valuable information if the motor basically gets jammed up and is not turning. Just something we want to do. You know what? Let's leave those two pins undecided. Let's not, because we could. Right now, I'll just leave them unconnected. So let's see here. So our ESP32, we got kind of a good map of what GPIO pins. So we don't really care about the IOs that they're connected to at this point in time. We're more likely we only are gonna care about the ports. So the next step we could want to work in. Let's see here, because all of it needs to be done. So we can. Well, here, let me get rid of this random ground connection. Okay. It's hard to know what direction you want to go in, because we have to define our circuits for the inputs and the limit switch. Technically, the limit switch is our inputs, but we're naming this just so we keep it better in our heads. We can suss out the RS-45, the other things, the programming interface. Let's go here. Let's see which direction we want to go in. Let's go and suss out the RS-45. It's gonna need to be done anyway. I think I'm starting to get a hang of this. So that's going to be no. I want to can I go to properties? Yes, I can go to properties. Here we go. All right. So this is going to be called RS-45. 45. We're just going to name the sheet. Okay. Save this guy. And there we go. Awesome sauce. So now I'll do the RS-45. Let's go ahead and bring in just a couple of power ports. I like to do that just because. Alright, so let's go back to Mausa. And here we go, RS-45. And we're back to where we usually go. We're going to download the CAD models. Alright, we're going to unzip you. You. Just copy that. Close that. Go to KiCad here. We're going to go to the footprint editor real quick. Here we go. Okay. We're going to import a footprint. Now, what's cool about this guy is, before I get too far, that's another standard package size SOIC 8. So it's going to make our lives a little bit easier. Okay, CAD. Yes, sir. There you are. File cannot be found. What in the world is wrong with you? Okay. File not found. Okay. Alright. Let's try. Let's get rid of this extra PDF there. Let's get rid of that. Let's re-download. Alright. Extract all. Let's see if KiCad, if it wants to be mad again. Import footprint. There we go. It might have just corrupted the zip file when I extracted it. Who knows? Okay. So we're going to save this SOIC-8. The components. Again, it's a standard footprint. And we're going to just use it as such. 3D models. Bam. Perfect. Save that. All right. Go back to KiCad and the symbol editor. Now we're going to go ahead and import the component. It's just easier this way. I'll import symbol. Oh, alright. File, import symbol. Man, you're being a little sussy today, KiCad. KiCad, alright. So, one of the things I typically will do is microchips, ICs. I'll usually give them a U prefix. That way, when we're going through part searches, they'll be easier to find. That way, you can filter based off of that. All right. Seems like no matter where I drag any of this stuff to, it doesn't care. The only reason I want to move stuff out of my way is because we're going to kind of clean this up a little bit. Well, you know, actually, this isn't too bad. Go ahead. Read out. And since we're going to be using ports for most of this, I think it'll be fine. We're not going to go through and clean that up too much. Files. Symbol properties. You know what? Here we go again. Let's save that. Yeah. Again, I should really format this or formalize this. That way I have to do this each time, or I should just do it ahead of time. That way I don't waste time here doing that screen capture, so it just makes it easier for me. Bye. Get rid of you. You're kind of wasting my time. Let's give you your proper footprint. SOIC 8. Okay. Okay. We want to give it a good description. All right. So let's see here. So this is technically an interface IC. It's an RS-42, 422, 45 transceiver, one driver, 4.75 to 5. Okay. So good. We'll have to, good, we'll need the 5-volt supply for that. Let's double check. Let's double check the data sheet on that. That might be for the VCC. Let's see what the VCC says here. Let's see here. Logic inputs. We're not looking at the logic, we're looking at the power supply. VCC. Maybe we want to choose a different IC because of the voltage. Which it shouldn't really matter. Let's make sure, let's see what the range is for the receiver. Let's see. The driver, we'll look at the GPIOs. I didn't catch that. That was my fault for not catching that. Let's see what voltage we need to for the okay. Driver input. Okay, looks like drive enable 3 volts, 3.3 volts. Okay. Looks like we can use it. We just got to make sure VCC is tied to 5 volts. So it's a good thing we have a 5-volt power supply in here. I just want to make sure that we're not making a mistake. Oh, looks like drive enable 3 volts. Okay. All right. So our control voltage from the ESP32 is fine. Good. It's still fine. We just go over here. Get rid of this little guy. And what did I choose? 5 volt. Just plus 5 volt. All right. Before I get too far ahead of myself here. Plus 5 volt. Okay. Boop. All right. So let's get back over here to the components. One driver, one receiver. Let's get rid of that. Okay, 4.75. Okay, RS-42, 45. Is there any other information we want? Negative 40 to plus 85. Make sure there's nothing else that we could put in here. No, that should be fine. All right. So we're going to manufacturer. I always forget. Max linear. Part number. All right. Vendor. Hey. Mausa. My bad. Me not paying attention. I'm trying to work too far ahead. I throw Val in here. Even though we're not going to use it, there's not going to be anything in there. We're just throwing it in here for consistency. Part number from the vendor is that. $2 and $4.84. Now again, before we get too far ahead of ourselves, let's go over to our Odo. We're going to add that. Grab our internal part number. Who said this wasn't a lot of fun? Let's track inventory. Blop, blop. Cost I've already forgotten. $1.02. Tax. Category. There's no actual category for that, so interface still good. Interface, okay. Now reference is going to be the description. Boom. Purchase. Mausa. Product code. Copy that again. Quantities of 1.0. Bump, 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 bump. Upload that. Bam. Alright. Now we're going to go. That looks like it's good. Okay. Read enable, drive input. Read output. Okay. Basically, this is your TX RX. CAB, that goes okay. That's doable. We can work with that. So we're going to save it. Go over to our schematic. Components. It's going to be U. Boom. U in here. Hello. Come on, drag you down a little bit. Hey, stop it. I just want to drag you down here. Right here. There we go. Alright. Okay, VCC. We want to kind of give this guy some bulk capacitance, so let's see what we've got here. That's 5 volt input. 4. 1206. 1210. It's 10 volts. So typically with capacitors, you want to go. So you want to try to take your voltage level and your the voltage capabilities of the capacitor. You at least want it to be 2 to 3 times the value. Well, a 10 volt capacitor would probably more than likely work. Let's not take our chances. Let's look for a higher voltage. So that's going to be. Let's just not. We might as well go and add something like an 0805. But let's see what we've got. Because it gave me a weird thing when I clicked on that directly. So Let's go 22 microfarad. 22 microfarad. We're going to apply that. Let's see here. Voltage reading. Can we at least get 25? 0805. There we go. 25 volts would be fine in my book. X5R should be fine for this guy. Let's see what that gives us. CA 64, 32. Murata's good. Murata, Kyocera, 32. Dollar range. Samsung Electromechanical. Since it's just a bulk power capacitor, yeah, we can go with the Samsung. That's fine. 0805. Let's go ahead and down that because we need the footprint. Okay. Blop. All right. So let's go ahead and create this guy. Let's go get the footprint. I'm going to file, import. Lots of fun, isn't it? Having so much fun, it's crazy. Maybe eventually it'll give us a tricky one to where S is going to be cap 0805. Well, the name it wants to give it is the actual official footprint. It's just easier to memorize them by the size 0805, the imperial size. 0805, file properties. Huh. Wow, look at that. Boom, boom. Save that. And we're going here. So it is another capacitor. I don't have any resistor. Oh, we have one resistor. So let's just copy this guy. We don't have to go through and fix it. Alright. So let's rename it. So let's get rid of this guy. So first it's 0805. 5 to 226, 22 microfarad. Let's see, 5. 104. What's the voltage of this guy again? It's 25 volts. 25. What is our tolerance? 20%. I think that was AAB. AAB 20%. And I think, if I remember right, it's X5R. X5R. Copy that. Boom. Save it. To go into footprint properties. Bam. All right. We're going to get that. The 0805. Bam. Nope. 010. 22. 25 volts. 20%. X5R. So I think it's negative 55 to 85. Negative 55 to 85. Rojas, it's not an automotive standard part, is it? No. All right. So Now it's a Samsung. Alright, Mauser, okay. Do that in there. Manufacturer and bam. And then you know what we get to do next is add this to Odo. Loads of fun, isn't it? So that's a Mauser part number. It's 10 cents and 043 cents. 10 cents and 0.043 cents. Okay. Now we get to go here to this lovely little thing. Products. Didn't have to go that way. We're going here. Bam. Sales. Passive. Oh, why you do that? Oh, why you do that, Odo? Purchase. Bowser. And that's unit quantity of 1. And if I'm not mistaken, Odo, you can set up your quantity breaks in here by just adding another vendor line and putting like quantity of like 100 and put its price in, quantity of 1,000. I think you can do that. I don't really mess with that. I don't really use Odo for price tracking too much. Mainly just for inventory. So I can keep better track of what I do have on hand. So when I do want to build a board or something. Alright, so we got that. Back to the schematic. And as long as I wasn't an idiot and saved it, yep, 805. Damn it, did I not save that? Was I an idiot? I was an idiot, my bad. Bam. It's like, why in the world is it showing the wrong description? Just because I was an idiot. Yeah, there we go. Just kind of give it a little bit of a bulk capacitance. 22 microfarads should be more than enough. Just to help with any transient voltages. Have this to help. Let's get rid of you. Let's go into another one because this might be crucial. And then 10 of I don't want that 104. The reason I'm throwing that 0.1 microfarad in is they help with noise on the power lines. Oh, all right. Hey, come on. Hey, he's being stubborn. Stop it. Stop. There we go. Don't mind me. Here. Oh, yeah, that's not too bad. Oh, get out of my way. Don't do that to me. Rotate you up nice and neatly. Throw you right here. Actually, I want more over here. Happy capacitors over here. Power supply here. Yeah, all right. Bam. Bam. Okay. So that'll plumb up the power supply to this guy. The IC4. You know what? We've got plenty of room on this sheet here. Let's kind of drag this up a little bit. There's no reason to make it busy. Now, because our connectors are going to be on the on another page. It's just easier that way. 45B, 45A. And it's bidirectional. Now we're going to. I gotta remember what. Let's see. So we need to make sure we. Let's see here. You are TX. No, that's not. It's 45. RX and TX. Let's read out. So it's 45. Read out RX. Should be 45 TX input. And it's going to be 45 DIR. That's going to be an input. So, let's read out the drive input. These guys, because of the way it works, you pop those two together because based off of the output mode of that DIR pin, either going to be in transmit mode or receive mode. Typically, you want to keep the UART chip on a peripheral device like this in receive mode, so it just waits for input, and then the central system, the microcontroller, basically handles all the flow. It reach out, says, "Hey, I'm looking for a device with this address, this device." All devices will pick it up. They'll read in the data. The bus will have the exact same signal. All devices will read in the same data. The microcontroller process, say, "Hey, I'm that address," and it'll send out its response, and the microcontroller is going to be listening to just that device. So that's how we're going to set it up and how it's going to be programmed now on. So we have our power supply, our kind of noise filter a little bit, and our bulk capacitors. And now we have our 45 chip. Like I said, these connectors we gotta separate 45 RX, DR, and TX. Let's double check. Alright. So that's our RS45. Let's go ahead. Not like super important, but I like just consistency of everything. 45. Nope. Okay. Save that guy. All right. So that's RS-45. Now, something we could do. Actually, you know what we're going to want to do here? You know, I don't want to oversimplify this, so I need to clean this up a little bit. Gotta give it some room. So I'm oversimplifying things, and I shouldn't. So one of the things we might want to do is also have. Where are you at? Use. I don't want that. All right. Okay. So we should throw a TVS diode, transient voltage suppressor, on the A and B pins, just to help sink down any spikes. Um, so let's go ahead and grab this guy. So it's a bidirectional, so it'll work perfectly. Let's grab the footprint. Very simple block diagrams. It's pretty crazy. Downloads. Extract all. Bam. Good thing is it's a SOT 23.3, which is another standard size. SOT is small outline transistor. Okay, so we have to lather, rinse, and repeat over and over and over and over again. Welcome to the world of engineering. Oh, wrong button. I want to import a footprint. All right, so we're going to go here to KiCad. Yes, there you are. All right. So that's that. And I said it was a SOT 23.3. So that would be the official size, but SOT 23.3 is much easier to remember. Properties. Huh. There's no model already thrown in there. All right. Please have a. Bam. All right. Okay. Save you. SOT 23.3. Now we get to go and. Ooh. Import the symbol. All right. All right. So. We're going to go and rename it. That way it fits a little bit better into our. So we're going to give it TVS. Give it the prefix of TVS. It'll just be easier to search. Control S. Okay, that's fine. That doesn't seem to matter because it'll go wherever it wants to go. File, simple properties, TVS, footprint. Let's go here. Let's give it the SOT 23.3. Delete, 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 delete. No data sheet. All right. All right. See, a lot of this is just fills up time. 4-watt peak. We're only really caring about Okay, but dual bidirectional. See, why are we repeating TVS multiple times? So we have TVS diode, its maximum voltage, 400 watt peak. All right. 26 volt is it'll clamp at 26 volts. So anything above 26 volts is where it automatically will clamp. And most TVS surges are going to be above 26 volts. They're automatically going to be above 26 volts. 12 volt working. That's fine. All right. Negative 55 to 150C. C to did I say 150C? Again, my brain is just not here. C Rojas. Okay. Now we're gonna add menu. Let's just add all the fields first. Be nice if I can actually. All right. So what is that? Borns, I think it was. Borns. Yes, sir, it is. Borns. Mauser. Their part number. $11 to 343. All right. Now we're going to go over to this guy. We're going to add a new product. Hooray for duplicity. That's going to be the internal part number that we use. Might as well go on to add this stuff. Mauser. Product code. $11. General information. Now, we don't have a category yet. We're going to TVS. And then our reference is its description. All right. So we have that added. Bam. Okay. Let's not make the same mistake I made that one time. So okay. Control save. This is fine. Your inputs and then your common, your ground, basically. So we just got that saved. Snap over to our schematic. Slap in the TVS diode we just added. You down here. All right. Okay. Snag onto these guys. And throw this guy right here. That way, if you accidentally uh, walk across the carpet, accidentally touch these two lines, the TVS will be less likely to hurt. The ESC discharge would be less likely to hurt this guy. It'll go through this diode and be passed safely. The other thing we're going to want to add is um, the ability to throw in a terminating resistor. We'll take care of that starting the next video because there'll be a lot more to cover. We'll set it up so a terminating resistor can be easily thrown in or enabled or disabled depending on how you want to use this device on the 485. So we'll kind of call it quits here. And I appreciate everybody tuning in. And leave any comments, ask any questions. I'll be happy to answer best I can. Thank you, and have a good rest of the evening.